Alright, in the last video I went over Charles Boyle's and Avogadro's laws individually, and those laws, as it says here, are very helpful only if other variables are held constant. So the Charles law works well, but only if pressure and moles are held constant, and Boyle's works great if temperature and moles are held constant. But what happens if multiple things are changing? Well, if that's the case, then you can take all of those individual gas laws and put them together, and when you do that, you get the combined gas law, which is this one right here. This one is not on your reference sheet, but it's one that is going to be pretty useful, and it's the one that I would recommend memorizing rather than memorizing all the other ones. And so when you use this one, you can just ignore any variables that are either held constant or are not mentioned in the problem at all. So for example, if you have a question that says nothing about the number of moles of gas and it says the temperature is held constant, then just ignore all of this and you get pressure and volume, which happens to be Boyle's law. Or if you have a question that says nothing about pressure and it says that the moles of gas are held constant, well, then ignore pressure and moles, and you get V over T, which is Charles' law. And if you happen to run across a question that says that the pressure, volume, and temperature are all changing, then you can just plug them all into the combined gas law and use that. Alright, so the combined gas law talks about gases that are changing. So you have an initial pressure and a final pressure, or you have an initial temperature and then you have a second temperature. But what happens if you have a gas in a container and its pressure or volume are not changing? We just want to know what the pressure of the gas is at one particular moment. Well, in that case, you can use what's called the ideal gas law. PV equals nRT. And so this up here is just a different variation of the same gas law, and oftentimes it's rearranged, and this is the one that's used most common. This is the one that's on your reference sheet. It's sometimes referred to as PV-nRT. The P stands for pressure, and it must be in atmospheres. The V stands for volume, and it must be in liters. The N stands for moles. T is temperature, and it must be in Kelvin. Now this R is a constant. It's called the universal gas constant, and it is 0.08206. The unit for R looks a little crazy. It's liters per atmospheres times mole Kelvin. And this unit right here is not something you need to memorize. It's on your reference sheet, but it's very important because it tells you what unit everything has to be in. So again, liters is for volume, atmospheres is for pressure, moles is obviously moles, and then temperature has to be in Kelvin. If you have any other unit in the question, then you must convert it to one of these four units. And you just plug it into PV-nRT and solve for whichever one is left. Now with a name like the ideal gas law, as you may remember from Chem 1, is that it's a hypothetical situation. Not many gases, or if any, are ideal. So we say that this particular gas law is obeyed by gases as the gases approach a low pressure and a high temperature. Now you can use this gas law always. Later on in this unit we'll talk about the van der Waals equation, which looks at real gases, but until that point you can continue to use the ideal gas law for any situation that it would be appropriate. Just remember that it's going to work best when you have a gas that is at a low pressure and a high temperature. Alright, and the last thing that I'm going to review in this video is gas stoichiometry. So gas stoichiometry pairs the ideal gas law with traditional stoichiometry that you have been using. And so there are a couple different things that you can use. Sometimes when you are at STP, which again stands for standard temperature and pressure, which is 1 atmosphere, and 273 Kelvin, or 0 degrees Celsius, you can say that there are 22.4 liters in 1 mole. And I'll show you that in a moment, how you can just plug that into stoichiometry. But if you're not at STP, you're going to have to combine the ideal gas law with stoichiometry. I'll show you an example of both of those in a moment. The other thing on this slide that I want to draw your attention to is this equation. Molar mass is equal to dRT over P. So some people call it the dirty P equation. And it allows you to calculate the molar mass of any gas if you have its density, temperature, and pressure. And so this little d is density, T T is temperature, pressure is the P, and it's derived from the ideal gas law, so this R is that same 0.08206. And because it's derived from the ideal gas law, the units are important. So temperature must be in Kelvin, pressure must be in atmospheres, and density is going to be in grams per liter. And again, that's just because we're using that universal gas constant that has liters in it, and this equation is derived from the ideal gas law. So we need to make sure to keep all the units consistent with that. And this one is not in your reference sheet, so it's one that I would recommend memorizing because it will be useful for you. All right, we'll practice some using the dirty P equation, and then we will look at some stoichiometry examples. So if you look at the first one, what is the molar mass of a gas? If 142 grams of the gas occupies 45.1 liters at 64.6 kPa and 25 degrees. So we're going to use this new equation. And if you start looking at the question and plugging in the numbers where they need to go. So molar mass is what you're looking for. We don't have density, but remember density is grams divided by liters, and we have both of those. So 142 grams over 45.1 liters. That's our density. R is that constant. And the temperature is 25 degrees, which you have to convert to Kelvin, so that's 298. And we have the pressure, but it's not in the correct unit. So we're going to do a unit conversion down here. So 64.6 kPa, and according to the ideal gas law, we need it to be in atmospheres. So in the unit conversion we did in the last video, 1 atmosphere is equal to 101.325 kilopascals. So if you do that cross multiplication, you end up getting 0.6376 atmospheres. And that's what will go on the bottom of our molar mass equation. And so if you do this math, you end up getting that the molar mass of this particular gas is 121, and the unit for molar mass again is grams per mole. So that is the final answer to that question. And just to check sig figs, we have all the numbers in our question have 3, so our final answer has 3. All right, and the second example. Determine the density of chlorine gas at 22 degrees and 1 atmosphere. So again, we're going to use that same equation. And if we start plugging in our numbers, density is what we're looking for. R is that gas constant. Temperature, we have 22 degrees Celsius, which needs to be in Kelvin, so that's 295. And our pressure is given to us in atmospheres, so that's the correct unit. Well, we're left with this number over here, the molar mass that we don't know. Well, it tells us chlorine gas, and so we can find the molar mass of chlorine gas. Remember that chlorine gas is a diatomic element, and so it comes in pairs, and so the molar mass for this would be 35.45 times 2. So 70.9 grams per mole would be the molar mass for chlorine gas. And then if you just do some math, you get that the density of this particular sample of chlorine gas is 2.93. And remember, the unit for density in this equation is grams per liter. And that will be your final answer. Alright, the last thing that I'm going to do in this video is go through a couple gas stoichiometry questions to show you the different types, to remind you of the different types that we did in Chem 1. So again, if it's at STP, you can use this new additional part, that 22.4 liters or in a mole of gas. If it's not at STP, you're going to have to use Pivnert and stoichiometry, and I will show you an example of both. Alright, so if we look at the first one, methane gas burns in oxygen to form carbon dioxide and water. How many grams of carbon dioxide can be formed if 1.36 liters of methane are burned at STP? So it's talking about a chemical reaction, so we have to first write the chemical equation. So methane gas burns in oxygen to form carbon dioxide and water, and then we're going to balance it. All right, and we're looking for how many grams, and so it's at STP, so that means we can use the 22.4 liters are in 1 mole. So I'm looking for grams of carbon dioxide, and I'm given 1.36 liters of methane gas. And so if we go back to stoichiometry, when grams is on the top, you're going to put the formula weight on the bottom times carbon dioxide's coefficient, which is 1. And because we're at STP, we can say that there are 22.4 liters in 1 mole of any gas, and we're talking about methane, so methane's coefficient goes on the bottom. And then you can just do your cross multiplication, and you get 2.67 grams of CO2. And that would then be your final answer. Next example, how many liters of oxygen gas will be needed to make 17.2 liters of water vapor at STP according to the following equation? The equation is there, but it's not balanced, so let me balance it really quick. And again, we are at STP, so we can just use that there are 22.4 liters in a mole, so X liters of O2, which is what we're trying to find. There are 22.4 liters in 1 mole, and so we can multiply it by oxygen's coefficient, and we're given 17 liters of water vapor. 22.4 goes on the bottom, times water's coefficient, and just cross multiply, and you get 8.60 liters of water vapor. All right, now for these examples, if you are not at STP, you got to do a little bit of extra work. And so if we look at the first one, so ethylene burns in oxygen. So again, it's a combustion reaction that we need to write the equation for, and then balance it. Okay, now how many grams of water can be formed at 1 atmosphere and 298 Kelvin if 1,250 milliliters of ethylene are burned? Well, this one is not at STP, so we're going to have to use Pivnert and stoichiometry. Because we're looking for grams, we're going to have to do stoichiometry last. So we'll do Pivnert first. So pressure, volume has to be in liters, so 1.25 liters is equal to moles we're trying to find. R is 0.08206. And the temperature is 298. So if we solve for moles, you get 0.05112 moles. Now we need to know what that's the moles of so we can properly set up our stoichiometry proportion. And if this is liters of ethylene, so we have liters of the ethylene, that means that this is going to be moles of ethylene. And from there, we can set up our stoichiometry proportion, and you can solve grams of water. So if moles is on the top, we're going to put 1 on the bottom times ethylene's coefficient, which is a 1. And grams of water is on the top, so I'm going to put water's coefficient on the bottom times its coefficient, which in this case is 2. And if you cross multiply, you get 1.8 grams of water. And that would be your final answer. And finally, this question, it is exactly the same. So we need to balance it real quick. And let's see, you're looking for liters of chlorine that will be needed to make 75 grams of the C2H2Cl4 at 1 atmosphere and 298 Kelvin according to this equation. Well, again, we are not at STP, so we're going to have to do stoichiometry and Pivnert. We are given grams, and so we need to do stoichiometry first. So 75 grams of C2H2Cl4. Grams goes on the bottom, so I'm going to put its formula weight on the top times its coefficient. And I'm looking for moles of chlorine gas. And I know I'm looking for moles of chlorine because I'm looking for liters of chlorine ultimately. Times its coefficient, and you do this math, and you end up getting 0.8937. And now I'm going to plug that into Pivnert. So you have 1 atmosphere times liters that we're trying to find, moles we just found, R and 298. Quickly do that math, and you get that the volume is 22 liters of chlorine gas, and that would be your final answer. So that is gas stoichiometry. This is all stuff you should have learned in Chem 1, so I'm going to expect that you know it, but if you have questions, look in your book, or you can always come in and ask me. I'll be happy to help you.